based on what we've done so far, we should already know what the graph of y equals log base 2 of x looks like. So we don't need to make a table of values, but if we wanted to, and it's not a bad idea to think about this, what are some values of x that we can plug in that we can evaluate easily? So give me a couple of values of x that work out nice for this equation. 2, 1. So if I plug in 2 for x, what do I get? Log 2 of 2 is equal to 1. What's log 2 of 1? 0. And remember, just a little memory thing here, I'll write it out bigger. When I'm figuring out this, I'm really figuring out the exponent. Log solve for exponents. So when I see log 2 of x, if I know that x is equal to 2, I'm saying to myself, 2 to what power is 2? 2 to what exponent would be? 2 would have to be 1. What's another one that you would know that would be easy? 4. So basically, and then 8, and so on. Basically, you're looking at your powers of 2. Now, how is the graph of log 2 of 2x minus 1 related to that graph? Now we're looking at our transformations. So for part B, and I'm going to change this word here. I think you can still see what's happening if you draw them on separate grids, and it's really easy to draw them on separate grids and still see that. If here in green, I graph my log base 2 of x. My table of values can help, but one of the things that we've already talked about is every log graph goes through the point 1, 0. And a secondary point, since the base is 2, it's going to go through the point 2, 1. And logs graphs have this shape with an asymptote at x equals 0. Over here in black, we're going to graph y equals log 2 of 2x minus 1. Now, to help us with that, it's just transformations. And we're going to go, just like we've done in transformations in every other unit so far, is work from left to right. Deal with all of our stretches and compressions first, and then do all of our translations next. So if I take the points that I know on my parent graph, which are 1, 0, 2, 1, and in the end we'll also look, does anything happen to that asymptote x equals 0? Moving from left to right, the numbers we hit, the first number we hit is the 2. Now be careful, we don't just hit, like there's 2 2's there. We have to remember that that 2, that's the base, that's part of our parent or our base graph. So it doesn't affect any of our transformations. That 2 tells us something about our initial points, that we have the point 2, 1, but it's not going to be a transformation. The first thing that we run into that is a transformation is the 2 in front of the x. So our only stretch or compression is affecting our x value because we have no vertical stretches or compressions. What are we going to multiply our x by if there's a 2 in front of that x? 1/2. The funny thing about the transformations unit is when you take it as our first unit, you learn all those things for the first time and you make some mistakes while doing it, and yet by the end of the year we do it so often that you feel like, oh, that was the easiest unit, because we keep reviewing it. So x by 1/2, that'll change this point to 1/2, 0, and this one to 1, 1. Then all of our translations, if we keep moving from left to right, we hit the -1. Is that going to move left, right, up, or down? It's going to move down. If they wanted that to move left or right, they would have added some brackets there. That would have moved things left and right. And if it was moving left and right like that, you would have had to remember, oh, I have to factor it out first. But without the brackets there, it's just moving down 1. That's a vertical translation. So our point is going to be 1/2, -1, and 1, comma 0. So we can put those points on our graph already. And this is what we have to start with. The next thing that we need to know is what happened to our asymptote. The important thing to think about with log graphs and a vertical asymptote at x equals 0, the only thing that's going to change that vertical asymptote is if it gets translated left or right. No stretches are going to affect it. No translations up or down are going to affect it. The only thing that's going to affect it is moving left or right. So we look here at our translations. Have we moved it left or right? No. So our asymptote is going to stay at x equals 0. Now that we have our points and our asymptote, we can draw the same shape. We can think there's been no reflections, so that makes sense that it would look like that, and we've labeled the 2 points. Finally, in part C, it says identify the intercepts. Well, we've got one x-intercept right here at 1, comma 0. As far as domain and range, use your asymptote and think I'm to the right of my asymptote, so that means x is going to be bigger than 0 for my domain. When I look at my range is everything. So now, just to practice some more of these transformation ones, I'd like you to turn to page 400. Page 400 should just be a blank one. Graph y equals 4 log base 3 of x plus 1. We'll do 2 minus 5. We'll do 2 more graphing examples, so I'll call this one A. So again, we've got transformations with the log graph. Step 1 is recognizing what's our parent graph, what's our base graph. So we need to look at our equation and say, my base is 3, so my parent graph is log base 3 of x. Quickly draw a sketch of that. You know the shape. You know that all log graphs go through 1, comma 0. And since the base is 3, it'll go through 3, comma 1. There'll also be an asymptote at x equals 0. Once you have your base graph, you can take your points, and we'll also look at our asymptote, and go through our transformations. So moving from left to right, deal with all of your stretches and compressions first. We only have a 4. That will multiply your y value by 4. Then your translations continue to move from left to right. We have that plus 1 and the minus 5. The plus 1 is going to move our graph left 1 unit. The minus 5 is going to move it down 5. So moving it left 1 to 0, down 5, minus 5. Left 1, go to 2, minus 1. And finally, we think about our asymptote. Again, the only thing that's going to affect our asymptote is moving things left or right. In this case, we have moved left 1. So if my asymptote was at x equals 0, now it's been moved left 1 to x equals negative 1. Oops. Beautiful. So then when graphing this, We're going to plot those points. I like to start by drawing in my asymptote. So there's my asymptote at x equals -1. I'm going to have 0, -5. By labeling that point on my graph, I'm telling everybody that the ticky marks that I made are going by 1s. I haven't indicated anywhere on my x scale yet, so by labeling this point to -1, I'm also indicating that my marks along my x-axis are going by 1. So I've provided a scale. Once I have these 2 points to draw the log graph, curve that down. Got to be careful here. They're picky. If you get sloppy, I kind of got a little bit sloppy there in that my graph crossed my asymptote. They don't like that because graphs aren't supposed to. So, here's some examples of some sloppy graphs. Maybe, whoa, went too far, get back over here. That's not a good idea. You're going to lose a half a mark for your shape. You're also going to, let's say you're approaching the asymptote. Just going to extend it here a little bit. You'll lose a half a mark if your graph looked like this. Oh, it looks really good, looks really good. Oh, wait a minute. Start going away from your asymptote at the end, you're going to lose a half a mark for that. Even though everything, had the arrow been here, it would have been perfect. And not drawn that extra part. But you're already turning the page and didn't even realize your pencil was still on there. So really looking at shape. See, what are other bad things that you can do for shape? Oh, you can do this for shape, that would be bad. Connect the dot, nice straight lines. It's curved, it's not straight. Like sine graphs. This is your sine graph, right? There's some exams that we mark that sine graphs end up like that. So you lose a half a mark for the shape of your graph. Okay, let's do one more. The hardest graphing one that I can think, well, I could think of harder ones, but this is about as hard as they could get on the exam. So we've got a natural log instead of a log. That makes it harder just because the base is harder. So what do we do with a natural log? Well, we start, same as before, draw our parent graphs. Every single log graph has the point 1, 0. What's the other point if you were graphing just the natural log of x? 10, 1 is on the common log. On the natural log, e, 1. All right? So we've got an e. So that already makes it just a little bit more awkward to work with. The shape still stays the same. The asymptote is still at x equals 0. But now when we're looking at our transformations, we have e, 1 and 1, 0 and x equals 0. So the e is one part that makes this one a little bit trickier. Just remembering that the base is e and then thinking, okay, e is equal to 2.7. So how do I deal with that a little bit? Because it's not a really nice number. What's the other thing that I put in this one that makes it just a little bit harder? Okay, so let's talk through transformations. Vertical and horizontal stretches. What am I going to have here? Y is going to get multiplied by 2. X is going to get multiplied by 2. So that's not bad. No fractions at least. So it'll be 2e. That's how you would write that. When you multiply e by 2, you get 2e, 2. And that doesn't look like an e yet. That's still bad. But we'll leave it. 2, 0. And we're not going to worry about our asymptotes quite yet. And then our translations. We have to move left, right, or up, down. We're going to go left. How many? 4. Good. Right? Whoa. That's the other part that makes this one hard, right? Okay? Can you see the 4? Right? This, if you just sort of, that looks like a 4. Is that why it's a 4? Okay, no, you have to factor it. Right, so I'm going to rewrite the equation again underneath. Anytime you have a horizontal translation and a horizontal stretch or compression, we have that with the half and the 2, you have to factor out. And this is where this one gets a little bit extra tricky, is how do you factor a half out of a whole number? Like, it's easy to factor 2 out of 8 or 3 out of 15, but a half out of 2, a couple of ways you can think about it. I find the easiest way to think about it is, say, pull out the half. I know the first one has to be x, and then imagine what number would have to be here. So I go half times that number is equal to 2. If I think about it that way, half times 4 is equal to 2, so you'll think of plus 4. If you think about it as a real-life example, what does it mean when I'm factoring a half out of 2? It's like you have a 2-liter bottle of Coke, and you want to trick your friends, and you've got 4 empty 500 ml bottles of Pepsi. You could fill 4 of those up with that 2 liters, because you have divided by a half liter. So 2 liters divided by a half liter would give you 4 of those smaller bottles. So now that we have that, we know that we're going left 4, and we're going to be going down 3. So how do we write left 4 when we have a 2e? 2e minus 4. Down 3 will be at minus 1. Left 4 will be at negative 2. Down 3 minus 3. If we think of our asymptote, again, the only thing that's going to affect that vertical asymptote is whether or not we're moving left or right. And so we are moving left 4. So our asymptote is going to be at x equals negative 4. So the factoring out on this one made this one a little bit more difficult. And finally, graphing it, the thing that we're going to have difficulty when graphing it is putting in that 1 point, which is a little awkward. As far as everything else, I would start with my asymptote. That's easy to put in. Looking at my 2 points, I would probably start with a point that's really easy to graph. Negative 2, negative 3. That's that point right there. And when graphing the other point, I know that my y-coordinate is going to be negative 1, 2e minus 4. So we remember that e is 2.71828, blah, 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 blah. Keeps on going forever. Maybe I would just think of it as 2.7. That's not too hard to do some mental math with. What's 2 times 2.7? 5.4. If I subtract 4 from 5.4, I'd get 1.4. So as far as labeling this point, I have 1.4 comma negative 1. And you can just sort of estimate where that would be, as long as it's appropriate. And now that we've got our points, draw our curve. Through those points, being careful not to cross our asymptote or not to loop away from it. And we have our final graph. All right, questions for practice are 8, 9, 10, and 11.